So in the second video, I'm going to talk about what to do with the energy that comes out of exergonic reactions. So the energy that comes out of exergonic reactions can be used to power endergonic reactions. So this is known as energetic coupling. So when a reaction goes from higher energy reactants, right, to lower energy products, okay, so this is the progress of the reaction, and disorder is increasing, this releases energy. And that energy, rather than being lost as heat in a cell, can be used to power reactions to take lower energy reactants to higher energy products. And two of these energetic coupling reactions I'm going to talk to you about today are called redox reactions and the transfer of phosphate groups. These are the two separate reactions I'm going to talk about. And we'll start with the redox reactions. So redox reaction is short for reduction oxidation reaction. And they're chemical reactions that involve the transfer of an electron. So oxidation is the loss of an electron, and reduction is gain of an electron. And a really easy mnemonic to remember the difference between oxidation and reduction is oil rig. So OIL, oxidation is loss of electrons, and RIG, rig, reduction is gain of electrons. These always occur together in these two half reactions. And the oxidation, right, as something loses an electron, it's exergonic. And reduction, if something gains an electron, is endergonic. So these two reactions paired together that always occur in these half reactions can be coupled to allow endergonic reactions to occur. So during there's two types of redox reactions. One involves the complete transfer of an electron. Okay, an example of this that we'll talk about is NaCl. And others simply shift position in their covalent bonds. So they can go from a non-polar covalent bond, right, Cc, to a polar covalent bond, Co. Okay, so let's talk about the complete transfer of electrons in a redox reaction. So here's a sodium atom here and a chloride atom. And what's going to happen is this electron here is going to be transferred, right? So it's going to be oxidized, right? Oxidation is the loss of an electron to chloride. And when chloride gains this electron, it's going to be reduced. So let's watch that happen. So sodium was oxidized, chloride was reduced. Okay, another example, right? So that was the first one, and it involves a complete transfer, is when electrons simply shift position in the bonds, okay? So let's take a molecule of glucose here, in which these electrons between carbon and hydrogen are equally distributed. Okay, and when you mix glucose with oxygen inside a cell, you'll get that glucose is going to be metabolized into CO2 and water, okay? Now this carbon that's in the glucose is going to turn into carbon dioxide, and the electron position is going to change. So it's going to go from equal distribution to being pulled closer to the oxygen. So in a way, this carbon has lost an electron, right? It's been oxidized. Well, oxidation is loss of electrons, okay? So this is one part of the reaction. This is oxidation, right? It's going to lose electrons, and this is going to release some energy that's going to power, right, this other part of the reaction, in which this is oxygen. These electrons are actually shared evenly, and they're going to be now shared unevenly. The oxygen is getting reduced, okay? So it's going to gain those electrons. You're going to create a more stable molecule, right, from something that had higher potential energy. And so you can see how these two half reactions, right, fueled the metabolism of glucose. So it's kind of, sometimes it can be kind of hard to see, right, when you have these transfer. The transfer of electrons is easy, but the uneven sharing is a little bit more difficult. You can also see this complete transfer of electrons when talking about electron donors and electron acceptors. So most electron acceptors, okay, so these are molecules that readily accept an electron, okay, and if they accept an electron, they usually gain potential energy as they are reduced. Okay, so we're gaining potential energy as we're being reduced. And electrons are usually accompanied by a proton. And so reduction, when something is reduced, it often adds an H to it. So I always say reduction, try to make an H noise in there. And then oxidation, removes the H's. Okay, so here's an example of an electron acceptor. So FAD is an electron acceptor, and it accepts 2 electrons to form FADH2. Okay, so here is a substrate with the 2 hydrogen atoms, and those are then transferred. This FAD then accepts 2 electrons and pulls 2 protons to form FADH2. So this FADH2 has been reduced. It has higher potential energy. Another example is NAD+. Okay, so NAD+ is an electron acceptor, and it's going to accept 2 electrons and 1 proton to form NADH. Okay, and so this NADH, if you follow the H, it's been reduced. Okay, and it has higher potential energy. And these electron carriers can then readily donate electrons to other molecules, thereby raising their potential energy. So the next thing I want to talk about, now that we're done talking about redox reactions, is energy transfer via ATP. Okay, so ATP stands for adenosine triphosphate, and it's the energy currency for cells. It provides fuel for most cellular activities, and ATP forms 3 bonds with, forms bonds with 3 negatively charged phosphate groups. And these phosphate groups with their negative charges repel each other. And they have high energy bonds that store a lot of potential energy. And so what is ATP? ATP is made up of an adenosine, which has a ribose, and an adenine. And we've talked a little bit about these. We talked about nucleotides, and then we have our high energy bonds and our phosphate groups. So this is ATP. So ATP hydrolysis, right? This ATP stores a lot of energy, and when it hydrolyzes, it actually releases energy. And we talked about this, right, when we did our delta G calculations, and we ended up with 7.3 kcals per mole of ATP, of energy being released. But it's not just released in cells. We use it to power other reactions. So here ATP stores energy, and when it's hydrolyzed, energy is released. And so ATP hydrolysis is transferred to a substrate by phosphorylation. So you're going to take off that inorganic phosphate and stick it onto a substrate. Okay, that's going to activate that substrate, and it's going to cause a change in the protein shape, and it can also raise the potential energy of that substrate. And so exergonic phosphorylation reactions are then coupled to endergonic reactions. So here's what that looks like. So we have an endergonic reaction in which we take the reactants A plus B, and we have to put some energy in to end up with the product AB. Okay, and so this reaction is endergonic. It has a positive delta G. We can couple this reaction, this endergonic reaction, with an exergonic reaction like ATP hydrolysis to power this reaction. Okay, so what's going to happen is in an endergonic reaction, ATP is going to be hydrolyzed, and it's that loss of that phosphate is going to get stuck to this substrate B here. And so we're going to end up with this activated substrate BP. Okay, now this has higher potential energy, BP, than this reactant here that's just B. Okay, and then this higher potential energy is this phosphate's gonna pop off, and then A and B are gonna be allowed to join. Okay, so then you're gonna have your product here, but you didn't have to input any energy. You just spent the energy of ATP to allow this reaction to occur. So another example of this is combining glucose and fructose to make sucrose. So this reaction, when it's not coupled, is energetically unfavorable. Okay, so the delta G is positive. It's an endergonic reaction. It has a positive delta G. Okay, ATP hydrolysis has this negative 7.3 delta G, and so we can make up for this energy input by spending some of our cellular cash or currency to make this reaction go. Okay, so we're gonna use this to still have an overall exergonic reaction. So what does that look like? Okay, so one of these phosphate groups is gonna be transferred to glucose, and so glucose is phosphorylated. This phosphorylated glucose has higher potential energy, and so when then it can combine with fructose, they can combine in an energetically favorable manner. Okay, so this reaction has an overall negative delta G. So what type of reactions are fueled in the cell by ATP? A lot of things. These are just some of the few examples. So when you want to pump anything against its concentration gradient, so this is called active transport, you need to spend some ATP. Some enzyme catalysis reactions, DNA replication, building proteins, these take ATP. They're not favorable reactions, so we couple ATP to make them occur. So just to summarize, redox reactions and the transfer of phosphate groups drive endergonic reactions. And then just again, a reminder, oil rig oxidation is the loss of electrons and reduction is the gain of electrons. Hint, hint. Okay, I look forward to seeing you in class, and thanks for your attention. Bye.